Again, remember that the formula for the regression is y hat beta 0 plus beta 1 x1 plus beta 2 x2 plus a number of beta n xn's with an epsilon of errors, with an epsilon term which represents our errors. And what we want to do is we want to know which variables or terms are really significant in the model. In other words, if they are significant, then there's a strong likelihood that we're going to keep them in the model. In our equation, we need to conduct a test to determine whether or not to keep a particular coefficient in the model. Remember that nothing is exact in our analysis. Everything is based on probabilistic tendencies. Thus, the beta coefficients are estimates of the multiplier effect of a particular x variable and its effect on the y variable. So we're going to use the simple regression to illustrate this point. So let's assume here that we have a beta 0 plus beta 1 x1 predicting y hat. If beta 1 is an estimate of the multiplier on x1, then multiplying b1 by x1 will give you the effect of x1 on y. In other words, if it's 1.2 times x1, then that means for every unit increase of x1, we will increase our predicted value of y hat by 1.2. So the question is, what if beta 1 is actually 0? Well, it should be clear that if beta 1 is 0, then the beta 1 x term multiplies to 0. And therefore, it has no effect on the predicted value, or y hat. So our goal really is to test whether or not beta 1 is actually statistically significant. In other words, if beta 1 has a possibility or probability of being 0. And you remember from other modules where we did confidence intervals, where we tested to see if a term or a mean was equivalent to 0 or not, this is basically the same test. So we can develop a hypothesis test to determine if beta 1 is actually 0, and we can do this for any terms. Now, we can assume that the distribution of the betas are close to normally distributed, and since they form a sample, we're going to use the t-distribution to estimate beta. If the betas have a t-distribution, meaning they're somewhat bell-shaped, we could then use the knowledge from previous modules to calculate a confidence interval for the beta parameter. And if you remember from the modules, we had this formula. We had some term, our point estimate, which in this case is beta 1, plus a t-multiple times our standard deviation of beta. If we compute b1 as the point estimate, we can calculate the standard deviation for the beta, which would be labeled as SB. And thus, we can compute a t-multiple based on the confidence level as well. Now, in Excel, the statistical applications are going to do this for you. But let's understand what's happening. Let's assume we want a 95% confidence interval for what was calculated as the point estimate for beta. And the value is 1.2. Now remember, your confidence interval is both on the positive side and negative side of 1.2. And that would mean that the value of beta could look like 1.2 plus or minus 1.7, giving us a confidence interval of negative 0.5 to 2.9. Now if we look at the range of the confidence interval, it crosses 0 because it goes from 2.9 all the way through 0 down to negative 0.5. This means there's a chance that the actual value for beta could be 0 given our 95% confidence interval. And since the confidence interval spans 0, it's possible that the coefficient is 0. And thus, we consider the term being not significant because this would mean that beta 1 has the possibility of being 0. And thus, if we multiply the 0 by x1, the term itself of x1 is not significant. So an easier way to look at this is to set up a hypothesis test to compute a t-statistic for the beta coefficient. So here we have our hypothesis test. H0 is beta 1 is equal to 0, and H1 is beta 1 is not equal to 0. Now in this case, we're using H1 as our alternative hypothesis. Some books will label it as H1, some will label it as HA. Our hope will be to reject the null hypothesis that beta 1 is 0. That meaning after we compute the t-statistic, we want to check the p-value to ensure that it is less than the confidence level, usually 0.05. And so the formula for computing the t-statistic is basically our t-critical value, this is our t-statistic, is equal to the beta 1 value that we have as our point estimate divided by the standard deviation of the beta term. Now, we could go old school and compare the critical value to the chart, but we're going to let Excel do the work. So in the past, we might have done this using our charts in a book or charts that we would have printed out for us, but we don't need to do that. On this slide, we show that Excel has calculated our beta coefficients and ultimately if they've calculated our p-values. So we have our regression equation, which is the complaints and sales as our two variables, x1 and x2. And we've asked Excel to compute all the measures. So first we're going to check beta 1. And we're going to set up our hypothesis test. Beta 1 is equal to 0 as the null hypothesis, and beta 1 is not equal to 0 as the alternative hypothesis. If we look at the T-statistic highlighted in the yellow along with the p-value, we see that the T-statistic has a value of 7.34 for the x1 variable, with a p-value of 0.00000018. Well, this p-value is clearly lower than 0.05. Therefore, we can reject the null hypothesis and state that b1 is not equal to 0. And thus, we could say that the complaints term is statistically significant. Now, you'll notice that even though we said it's 0.00000018, you'll notice that it says 1.8 e to the negative 07. It's important to understand that that is scientific notation, so it would be 1.803 times 10 to the negative 7th power. So we would actually move the decimal place 7 places to the left. Now, if we take the same approach for sales, we see that the p-value is 0.008. And therefore, we can also reject the null hypothesis for the sales coefficient and state that that term is statistically significant.